Okay, good afternoon, everybody. Okay, last time we just finished the section chapter 9.1 and 9.2. Again. The chapter 1, chapter 9.1, two proportions, and chapter 9.2, paired samples for two means. And today we are moving to the chapter 9.3 about dependent samples for two means. Oh, why no projection? Let me. Okay. And again. The first one, for two proportions, it can be two situations, and pair the samples for two means. For example, if a new drug has been discovered for a couple of years, and the doctors or the experts want to know how the drug treat people, does it work, and some side effects or something like this, and they can run the paired t-test. And today we are discussing something about independent samples for two means. Okay, this section will look at how to analyze when two samples are collected that are independent. As with all other hypothesis tests and confidence intervals, the process is the same, though the formulas and assumptions are different. The only difference with the independent t-test as opposite to the other tests that have been done is that there are any actual two different formulas to use depending on if the particular assumption is made or not. Okay, hypothesis test of independent t-test, two sample t-test. Okay, first, state the random variables and the parameters in words. X1, the random variable 1. X2, the random variable number 2. Mu1, the mean, the average, or we call it average, of random variables 1. And mu2, the mean of random variable number 2, and set the non-hypothesis and alternative hypothesis, and the level of significance of the normal hypothesis will be first one, non-hypothesis, they are equal. And there are three possibles in the alternative hypothesis. The first one, the mean 1 smaller than the mean 2. Mean 1 is greater than the mean 2. Mean 1 is not equal to mean 2. Sure, we can list the possibility of there are three. And the first, the non-hypothesis is mu1 is equal to mu2. Okay. State and check the assumptions for the hypothesis test. A random variable, random sample of the size n1 is taken from population 1. A random sample size of n2 is taken from population 2. Okay, note the sample do not need to be the same size. Yeah, actually, under some situation, it's difficult to test to get the same number of the sample. Okay, but the test is more robust if they are. They are. Okay. B. Two samples are independent. C. Population 1 is normally distributed. Population 2 is normally distributed. Just as before, the t-test is fairly robust to the assumption if the sample size is larger, and the 30 samples is the minimum choice, minimum requirement for this. Okay, this means if this assumption isn't made, but your sample size are quite larger, over 30, then the results of the t-test are valid. D. The population variances are unknown and not assumed to be equal. The old assumption is that the variances are equal. However, this assumption is no longer an assumption that most statisticians use. Excuse me. Oh, yeah, sorry, I got a flu, so when I close to students, I will wear my mask. But now I'm safety distance away from you, so I didn't wear the mask. Okay, next. Excuse me. Find the sample statistic, test the statistic, and p-value. The sample statistic calculate x bar 1, x bar 2, and s1, s2, n1, n2, and the t-score is x1 minus x1 bar minus x2 bar minus mu1 minus mu2, and in the denominator is a little bit like this, and sure, for me, for you, this formula is a little bit complicated, so I will tell you, I will calculate it by hand, then I will encourage you to use the online free applications to calculate that. Okay, the p-value, use this. Okay, then if HA, the alternative hypothesis, the lower limit is like this one, upper limit is your statistic. If non-hypothesis mu1 is greater than mu2, the lower limit is your test statistic, and the upper limit is this one. Okay, let's move to next one. Use R. Actually, we don't use R because R is a very professional software. And here we use the online applications and Google Office. Conclusion: there is where you write reject non-hypothesis or fail to reject non-hypothesis. The rule is if p-value is smaller than alpha, then reject it. If the p-value greater or equal to alpha, then fail to reject the non-hypothesis. Interpretation: this is where you interpret a real-world term, the conclusion to the test. The conclusion for a hypothesis test is that you either have enough evidence to show the alternative hypothesis is true, or you don't have enough evidence to show that is true. Okay. And confidence interval for the difference in means from two independent samples. Okay. The confidence interval for difference in means has the same random variables and means that the same assumption as the hypothesis for completing the confidence interval step. Look like this. Find a sample statistic and confidence interval like this one. Sure. Later, some easy parts I will encourage you to calculate by hands, especially use the applications. For example, the calculator, online calculator, or online apps. But for some complicated parts, I encourage you to get the answer from the applications. Okay. Then next. Okay. Statistical interpretation. In general, this looks like there is a C% chance that the lower limit minus E smaller than mu1 minus mu2 smaller than x bar minus x bar 2 and plus E. Okay, contains the true mean difference. The real-world interpretation, this is where you state what the interval contains the true difference in means, though often you state how much more or less the first mean is from the second mean. Okay. How to check assumption of two sample t-test and confidence interval. In order for the t-test or confidence interval to be valid, the assumptions of these tests must be true. So whenever you run a t-test or confidence interval, you must make sure the assumptions are true. So you need to check them. Here is how you do this. First, for the random samples assumption, describe how you took those two samples. Make sure your sampling technique is random for both samples. No bias. Okay. Second, for the independent assumption, describe how they are independent samples. Third, for the assumption about each population being normally distributed, remember the process of assessing normality from Chapter 6. Make sure you assess each sample separately. You don't need to check the equivariance assumption since it is not been assumed. Okay, let's check the question. After we practice the question, it will be easier to understand this. Okay, example 9.3.1. Hypothesis test for two means. Okay, the cholesterol level of patients who had heart attack was measured 2 days after the heart attack. Okay, again. 2 days of the heart attack, the cholesterol level has been measured. Okay, the researchers want to see if patients who have heart attacks have higher cholesterol level over healthy people. So they measured the cholesterol level for healthy adults who show no sign of heart disease. The data is on the table 9.3.1. Cholesterol level. After the question, do the data show the people who have heart attacks and have higher cholesterol level over patients that have heart attacks test at a 1% level? 1% level. Okay. And now let's check the number one by one. Here, okay. Just check that 270, 236, 210, like this one. And the second one here. Cholesterol level of healthy individuals 196, 232, 200, 242. Roughly, we can say anything because check the number here. Check it. Roughly from the left column. Generally speaking, more numbers are over 200. But from the right column, 196 to 11111. It seems that the cholesterol level on the right column, it means the healthy individual, the cholesterol level, a little bit like that. The level is lower than the left one. Okay, sure. It's just our observation without any scientific calculation. Just observation. Okay, let's check that. Let's check it. First, state the random variables and two parameters in words. Okay, first, cholesterol level of patients who had heart attack, that is X1. And X2, the variable is cholesterol level of healthy individuals. And mu1, mean cholesterol level of patients who had a heart attack. Mu2, mean cholesterol level of healthy individuals. Okay, and second, state the non-hypothesis and alternative hypothesis and the level of significance. Yep, the first, non-hypothesis, the mean are equal. I mean, the mean of cholesterol level from 2 days of the heart attack patients are equal to the healthy people with their cholesterol level. Okay, this is the first hypothesis. And the non-hypothesis, they are not equal. They are not equal. Okay, especially here, the mu1 is greater than mu2. It means it implies the heart attack is highly related to the cholesterol level. Okay, let's check. 3. State and check the assumption for hypothesis test. Okay, a random sample of 28 cholesterol level of patients who had heart attack is taken, and the other side for healthy people, the random sample is about 30 samples has been taken. Okay. The problem does not state if either sample was randomly selected, so this assumption may not be valid. Okay. It means it didn't say anything. Okay. The two samples are independent. This is because they were dealing with patients who had heart attack or healthy individuals. They are not paired. Samples. They are not paired t-test. So don't worry about that. C. Population of all cholesterol levels of patients who had heart attack is normally distributed. Okay, then population of all cholesterol levels of healthy individuals is normally distributed. Okay, those are normal distribution. Okay, and here, patients who had heart attacks, like this one, the distribution 100 to 150, 150 to 200, 200 to 250, like this one. Oh, we can observe it. Most cases are falling on 200 to 300. Okay, for the cholesterol level of the heart attack patients. Okay, let's check next. And the box plot looks like this. The normal quantile plot of this looks like this. And let's check the other side. The cholesterol level of healthy adults. We can observe that the type 1 and 2, the level is from 180 to 200. 180 to 200. Compared to the previous one, it is concentrated on the 200 to 300. Okay. This does not look bell-shaped. Again, this does not look like bell-shaped. But previous one, this one, yeah, this looks somewhat bell-shaped. Normal distribution as a normal distribution. But for the healthy people, the cholesterol level, the distribution, not a bell-shaped. Okay. And here's the box plot. There are no outliers. Okay, this doesn't look linear. And now let's check it. First one, the sample statistic X bar 252.32, and this like this one, and within the calculation, okay, and now let me show you how to do this. Copy, and we can move. Okay, let me finish this question, then we can have a break, okay? Okay, we can move here. Okay, sorry. Okay, just switch the interface to English. A new, uh, 9.3.1. Okay. Okay, we got the cholesterol level here. And now we know here I use the, maybe, there are 28 patients here and 30 normal healthy people. No. Okay, and now first one. First, to calculate S bar means the average of that one. Okay, we can use this. Here mean. Okay, and you can check this. Click here and move to the function column. Click equal and type average. And select the range as we want. Yeah, get it? Sure. I use the Google Office and I got the answer is the average should be 253.92, but I have no idea where does it come from. Where does it come from? Okay, we don't care about it. Okay, we can move to next one. Next one, have the symbol equal, average, and here, and select range, and click. Yeah, sure. And the answer here is the same as this one, And to be honest, I have an idea where we have different x bar 1, but it doesn't matter. It doesn't matter. Here is the x2 bar, 193.13. Okay, and next, calculate the S1 standard deviation, and we can type here and type here. Click standard deviation 7.71. 47.06. I have no idea why we get different answer, but very close. We can ignore this part. And the second one, yeah, the same. Click here and move here. Click equal standard deviation dot yeah, 22.300, like this one, no problem. And N 28 and 1. That's 28. And 2, that is 30. Okay, and now we have the basic information. Yeah, I try to use the Google Office to calculate those important factors. And next, how to calculate the t. And now I encourage you to calculate by, like me, I use the calculator, but with some functions like this. The t-score like this. Okay, I just use this one. Okay, 252.32 minus 193.13 minus 0. Generally, that is 0. And divided by square root of here, standard deviation square divided by n1 standard deviation square divided by n2, and the t-value is close to 6.015. And the degree of freedom here is a little bit complicated. And the A, about this. B, like this. The degree of freedom about 37. Yeah, sure. Like this one, after the calculation is about this one. And the p-value the p-value is very small, very small, like this one, Okay, let's move to the conclusion. The T, that is 6.1452, degree of freedom 37.675, p-value 1.86 to the 10 of the power minus 7, and alternative hypothesis that is true difference mean that is greater than 0, and the 95 confidence interval is this one. Okay, thus we have strong evidence to reject the non-hypothesis. There is enough evidence to show the patients who have heart attack have higher cholesterol level on average from healthy individuals, though to realize that some of assumptions are not valid, so this interpretation may be invalid. Okay. Sorry to bother everybody a little bit, and please have a 10-minute break, then we will come back later. Okay, see you later.